Okay, so since we lost half an hour, so what I will do, my plan is to do cut down on one thing. So I will do binary search trees and balanced binary search trees, and then after the break I will try to do something more interesting. I'll try to do this union find data structure. So we'll mostly care about how to do balanced binary search trees. So what is a binary search tree? A binary search tree is a data structure. So first of all, it's a binary tree. So and second, what we can do is the other property of a binary tree is that it maintains a linearly ordered set of elements. So linearly ordered in some dynamic manner. So what does this mean? This means that elements can be inserted or deleted, right? So you want to maintain some linear order, but you want to allow elements to be inserted, elements to be deleted, right? So add their phone numbers, you delete their phone numbers, right? So this is and you still want to, when you open the list of phone numbers, you get them in an alphabetical order. So this is a natural use case where you want to maintain a linearly ordered set of elements, say the names of people and their phone numbers in, let's say, an alphabetical order, where you're allowed to you want to be allowed to insert new names and delete new names, but you want to maintain this in an alphabetical order. Right, so why would you want to maintain it in an alphabetical order? So that you can do binary search and quickly find a name that you want. Okay, so let's start with that problem. So suppose you want to implement something like this. How would you go about implementing it? So a natural idea is to use an array, right? So suppose we just use an array, right? So you have n elements and these are sorted in increasing order, let's say. Okay. So now if a new element arrives, let's say 3. Okay. So new element 3 arrives, then suppose we just use an array, then you have the following problem that you will have to, let's suppose that you have a little more space in your array, then you have to shift all these elements right one by one and then insert the element 3 in its right position. So in this case, if you want to insert, takes of n time, right? So if there are n elements and you want to insert a new element inside your array, then you have to shift everything by one, assuming you have enough space in the array left, and then you insert the new element, and this takes linear time, right? So similarly, if you want to delete an element, you want to still, because it's sorted, you can take log n time to find it, but you still need to delete the element and then shift everything to the left. So you spend a search of log n time, but you spend linear time in maintaining this data structure, right? So okay, so do this insert, which is do, so let's say sorted array and search, then shift right, so let's say insert x, shift right all elements in array, larger than x, okay, and place x in its correct position. So this step takes O of log n time, but this step dominates it and this takes linear time. So what we would like to do is to design a data structure that sort of decreases this time, the insert time and similarly the delete time to also log n. Okay. And so what we could do is, if you have n elements, we could build a binary tree. So binary tree has the property that for all x, so the binary tree is a binary, so every node has at most 2 children, so it's a rooted tree. This is a rooted tree where every node has at most 2 children, right? And suppose and what is the property that we have? If we look at a node x, and if you look at the left and right subtrees, then for all y in T left, y is okay, so less than or less than equal to x, and for all y in T right, right. So if T left is the subtree rooted left child, T right is the one rooted right child, then we have the following property that for every node here, this is smaller than x, every node in here, this is smaller than this is larger than x, right? Okay. So what do we know? So given n elements, there exists a BST, a binary search, let's call it BST, of height theta. So if I give you n elements, you can always construct a binary search tree whose height is at most log n, right? It has to be at least log n, and we can show that we can always construct its height at most log n by let's say picking a median element at each step and recursively computing the BST for the two parts. Okay. So the problem is we would like to so this is good as long as the elements are static. So if there are no insertions and deletions, you can of course build a binary search tree, and now your search time is log n because the search time is dependent on the height, so or the depth of a node. So the path from the root down to any of the leaves. This is the amount of time it takes to search, and so BST of height log n has search time of log n. Okay, so the problem is now to sort of maintain this property with the additional constraint that with the additional features that you want to insert elements, you want to delete elements, and yet you want to maintain that maintain that the tree is balanced. So in particular, so we want to maintain a balanced BST under insertion and deletion. So this is our goal. So one thing I want to do is to define what it means for a tree to be balanced. So a tree is balanced if the height is okay. So we just want to ensure that this binary search tree has a height that is O of log n. So it could be 10 times log n or 2000 times log n, but it's sort of, as long as it's O of log n, we are happy. So search time is still logarithmic in the number of elements, and that is exactly what we want. So we want to ensure that the tree is balanced, okay, and by balanced we mean that the height of the tree is at most O of log n, where n is the number of elements in the tree. Okay. So now let me ask you the following question. Okay. Let suppose suppose T is a, let's say, a BST such that for all nodes x, x has either exactly 2 children or no children. Suppose I give you a tree, I give you BST, I give you the following property. I tell you that look at every node, it has exactly 2 children or 0 children. Okay, this is the property that this BST enjoys. Now, is it true that if this property holds, then the tree is balanced? By which we mean that is it true that as long as this property is sufficient to ensure that the height of the tree is O of log n? No. Okay, so is there an example? So if you want to try it, okay. Okay, fair enough. So you could build a tree like this. Now, if you have n elements, you can see that the height is linear, right? So such a condition is not sufficient, right? So the answer here is not balanced. Right? So the tree is not balanced. So let me ask you another question. Okay, so again T is a BST. The average depth of a leaf is O of log n. Okay, the average depth of a leaf is O of log n. So you look at each leaf and you look at its height and you take the average of these.
The question is, if it is not balanced, this one is not balanced, what to do with this?
Sorry?
If it is not balanced, what to do in that case? How to balance it?
Oh, that's what we'll do. So we'll come into that. So at this point, I'm just motivating the following fact. So let's look at the definition. What would you require for balance? So if you impose the following condition.
Definition of balance because balance tree should have a slight difference.
You see, balance by balanced, we only mean that the height is O of log n. That's all we want. Okay. This is the condition this is how we define that the tree is balanced. Now we are saying, well, suppose we impose the following local condition on every node. It has 0 children or 2 children. Is this sufficient for the tree to be balanced? And the answer is no, because even if you impose this condition, there are trees that are not balanced. So this is not a good enough notion to sort of go ahead with. So now what about this? So if every leaf has if the average depth of a leaf is O of log n, then is it sufficient for is this a sufficient condition for a tree to be balanced? Yes? Okay, so how would you prove this? No? Okay.
Because the leaf, for example, if we refer to this tree, then the leaf which is leftmost on the top, the height will be lesser and the lesser than log n. The average will come out to be log n in this case also.
Is the average log n?
Average of height of leaves.
Okay, so let's look at the height of these leaves. So what is the or the depth of the leaves? So this is let's say depth 1, 2, 3, 4, 5, and so on. But the average of these numbers is about n over 2. No, the average. So average is about n over 2. Right? If you essentially, if there are, okay, so what is the average? So if there are n leaves, if there are, let's say, if there are n leaves, right? So for every leaf there is a parent, right? So the number of nodes is 2 times the number of, okay. So if there are n leaves, then the average height or depth is sum over leaves, the depth of a leaf divided by n, okay, or number of leaves. So here this would be the sum of these numbers, which is about n into n plus 1 over 2, right, divided by the number of leaves, which is about n. So this is about n over 2. Okay, but I'm saying that the average depth is log n. Okay, if the average depth is log n, is it true that the tree is balanced? Is it true that every node must be at depth log n?
Height is the maximum depth. Depth is about the leaf, and then when the leaf is at the lowest limit, like it's at the maximum depth.
Huh.
So if the average depth is auto log n, so that means the tree height will also be log n.
Okay, so what is, okay, again, so the depth of a leaf is the length of the path from the root down to the leaf. Now what we are saying is the average depth is log n. So if you go down to each leaf and you look at the depth and you sum all over all of these and divide by the number of leaves, this is about say 2 log n, 10 log n, or some O of log n. But what does it mean for a tree to be balanced? For a tree to be balanced, every path from the root to the leaf must have every leaf must be at depth O of log n. So every path must be O of log n. So now I am asking the following question: if the average is small, if the average of the depth is log n, should it be that everything is log n? If the average is small, should all the elements be small? No. So if you're in your class, if the average rank is very low, doesn't mean that everybody is performed poorly. There might be a few bright sparks, but on average it would still be low. So this is what we are saying. You see, this is not sufficient condition for a tree to be balanced. I could say the average depth is log n and yet have a node of high depth. Okay, and so that the tree is not balanced. So can you give me an example? This is not true. So could you construct a binary tree where this is
You can have some nodes which have very less height, but not such which has very,
okay?
which has a large part.
Okay. Yeah. So that's roughly the idea. So you could do something like that. Sort of a binary tree. So this is sufficiently balanced, but there is, let's say, one long path down to this leaf.
Yes, so
This is a binary tree, right? I just put one path down all the way to this node. Yeah, sure. I mean, I can put numbers so that it's a binary search tree. Right? So you see, all of these guys have a very small depth, but there's one node that has very large depth, so that sort of it doesn't affect the average, right? Because there's only one node whose value is large, but the height of the tree is the tree is not balanced, because if your search is trying to look for this node, then you will end up spending linear time. Okay, so you could try to construct such an example. Okay. Okay, so what we would like to do is to maintain a balanced search tree. Now the unfortunate thing is that all of these structures that we drew here and the one that we drew here could arise in practice by a sequence of insertions. Right? If you just have a poor sequence of insertions, you could end up with a tree that is completely unbalanced, right? Like this example, or even something much worse, which is that you insert elements in the sorted order and you get essentially a list, a linked list instead of a tree. Right? And the depth is linear. Right? So now I want to claim the following. I'm going to give you another definition. So each node x if height of left of x minus height of x, this is at most 1, then T is balanced. Okay, I claim the following. We are going to impose the following condition, that if you look at any node, the height, which is number of hops, okay, max number of hops to a leaf in this subtree. So the height of a node x is the maximum overall maximum number of hops you need to go down to a leaf. Right? So if I impose that for every node in the tree, I look at the left child and the right child, and their heights differ by at most 1, then I claim that this is sufficient. This implies the tree is balanced. Okay, so this implies T is balanced. Okay, and a binary tree, so the okay. Okay. So a binary tree that maintains this invariant is called an AVL tree. So this is after this, I forget this and this. So this is I think from the 1970s or so, and this is the first balanced binary search tree. Okay, so what we will maintain in an AVL tree is that the height, for if I look at any node, if I look at the left child and the right child, their heights differ by at most 1. Okay, we are going to impose this condition. We are going to maintain this as invariant. So, of course, we will see how we can maintain this as invariant. The claim is that, the first claim is that if you do this, then the height is log n. Okay, and then we will see algorithmically over insertions and deletions how we can maintain this. Okay, there are two parts. The first part is that if this condition is true, then the height has to be log n. You cannot construct a binary search tree whose height is much more than log n. The two conditions we started with, these are not good enough, but this is good enough. Okay, that's the first part. The second part is how do you maintain this? Over insertion, so now you are in an algorithmic process that says that if I insert something, if I delete something, I can still maintain this property. Okay, and not only that, I want to maintain this property efficiently. So I want to do it very quickly. So insertions and deletions, we want, you remember, we wanted to, the whole thing to be done in log n time. So, you know, you want to maintain this property over insertions and deletions in log n time. Okay? Okay. So, what else did I want to do? Okay, so let's do this before we. Okay, so let me ask you the following question. Okay. Okay, so let's say n sub h is the minimum number of nodes in an AVL tree of height h. Okay, so we want to know, you know, so for example, if you look at the worst case situation of an unbalanced tree, which is just a path, and if this tree has height h, then the number of nodes is h, right? So it can be so, the tree can be so sparse that if the height is h, then the number of nodes is h. Now I want to show you, so I want to first claim that the tree spans, so I want to instead show you that if I count the number of nodes, the minimum number of nodes in an AVL tree whose height is h, then this quantity is large. This quantity is exponential in h. Okay, if this quantity is exponential in h, and then you can just take the inverse function and show that the depth is log n. Okay, so we want to compute this quantity. So the property we have is this. Okay, and we want to compute n sub h, the number of nodes, the minimum number of nodes in a tree, in a tree of height h, given that's an AVL tree. So how would you compute this quantity?
H equals to log by induction.
Okay, so there is induction somewhere. One could use induction there. Induction is a good answer. But let's see, how can you construct an AVL tree that has the minimum number of nodes? Among all AVL trees of height h, I want to pick the AVL or one AVL tree with the fewest number of nodes.
The last level contains only one node.
Okay, so we could do it bottom up. Let's say, so we can build this node, and so this is an AVL tree, right? So this is the root, and this has one child. Okay, okay. So the other convention, okay, yeah, okay, right? So this is an AVL tree. So you might want to do something like that. So that's the root. This is not an AVL tree. So we could add one more child here, right? So we can sort of stare at this and say that, you know, this must be the smallest, the sparsest AVL tree, the AVL tree with the fewest number of nodes, whose height is 2. Right? You must have 4 nodes. But now, how would you come up with how would you compute something like this? Huh? Recursion. Okay. So let's try to write the recursive formula. So can you write a recurrence relation for the number of nodes in a tree of height h?
In the left tree plus number of nodes in the right.
Uh-huh.
Plus that would be
Plus.
number of nodes in the current.
Okay. So the number of nodes in a tree of height h is the number of nodes left, right? So the number of nodes in the left subtree, but this guy has height h minus 1. Right? So it's just the minimum number in a minus 1. Okay? And this is h minus 1, and this guy is at most, is at least h minus 2. Right? So n sub h minus 2 plus this guy. Okay? So now we have this recurrence, and if we solve this recurrence, we know that, okay, so we know that the number of nodes in a tree, minimum number of nodes, is at least this much. Right? So this is clear? Okay. So now this is a ugly number, it's sort of dependent on two terms, and now we don't know how to do it. All this master method kind of things don't help us. So what do? How do we solve this recurrence?
It's like by induction and
Okay, you could do induction. Okay, so it should immediately exactly. So this, so you should okay. So if you stare at this, you should immediately. This should be familiar to you because it sort of looks like a Fibonacci series, almost. But we got except for this plus one, right? So what is the Fibonacci series? Fn is equal to Fn minus 1 plus Fn minus 2. Right? This looks exactly like that. N sub h is, okay, well at least n sub, okay, so is at least n sub h minus 1 plus n sub h minus 2 plus 1. Right? So what can we do? We can ignore this. Because you're only asking for how, you're looking for a lower bound, so you can say, well, yeah, so sure, n sub h is at least n sub h minus 1 plus n sub h minus 2. So you can't be wrong, right? So it's at least this plus 1, but this plus 1 is not going to add too much, so we can just say this is at least this much. Right? And now what do we know about the Fibonacci series? What do you know about the nth term, or the hth term of the Fibonacci series? How large is it? We know that it grows exponentially, right? So okay, so now we can say, let's say guess that, so we can just plug in the Fibonacci series, so is at most, so what is at least, so let's say phi to the n or something like that, right? Where phi is the golden ratio. So it's about this much, right? So it's not entirely accurate, but this is sufficient. So what does this mean? So this is phi, so essentially for us this is sufficient. Because it says that if you have a Fibonacci series of, if you have an avial tree of height h, then you know that the number of, this is phi to the h, right? Then the number of nodes is some constant to the h, right? So the number of nodes in a tree of height h is at least, let's say, phi to the h. So now if you take log, then the log, let's say, base phi, then we know that at least h, so the height is at most log of the number of nodes, right? Okay. So we proved the first part, that if you just impose this condition, then you know that your tree is balanced. Right? Is this clear? So you are saying, like, okay, so let's look at a tree of height h, and let's see what is the minimum number of nodes in such a tree if you impose the AVL condition. Well, you have this recurrence, and this tells us that the number of nodes in a tree of height h is at least 5 to the h. 5 is the golden ratio, is a constant. We don't care what the constant is, but it's a constant. So the number of nodes is at least 5 to the h, just take log. So therefore, the height is upper bounded by log of the number of nodes, which is exactly our definition of balance. Right? So therefore, if you impose this condition, then your tree is balanced. So this is a good condition. Yeah. Okay. So I can tell you one more trick. So one way, another sort of quick and dirty way to solve this recurrence is the following. If you don't suddenly recognize Fibonacci numbers, well, n sub h, we can assume, if you stare at it, it's not hard to prove that n sub h must be monotonic. The number of nodes in a tree of height h should be at least the number of nodes in a tree of h minus 1, and so on. Right? So we can now say that this is at least 2 times n sub h minus 2 plus 1. Right? This quantity is at least as large as that, since your low bounding this is this, and so now we can drop this as well. So n sub h is at least 2 times n sub h minus 2. Right? And from here, this is patently obvious how to solve, and now you get a much simpler recurrence because you're only after lower bounds, and this is also sufficient to show that the height is log n. So this will give you something like 2 log n or something as the height, but this is slightly sharper. But that's only in constants, and okay. So now we've shown that if you impose a condition, we get balance. So now,
Golden ratio is roughly 1.6, I think.
yeah.
So that means it will be better than shouldn't it be log 2? How can it be better than log base 2?
So okay, so if you do this, you get a height of about 1.4 blah 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 times log n.
Log base, I mean,
Log
1.6.
log 2. So if you this is log 5, but I think if you do something else, so then you get that the height is at most something like 1.4 blah 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 log n to the base 2. So you get an additional multiplicative factor of 1.4 something like that. So this is log to the base 5. So I'm going to. So I'm taking log to the base 5 on both sides. So we know that log nh to the base 5 is at least h. So in terms of log 2, this is log 2 to the.
But we have a tighter bound in form of rho and log to the base 5. So that is a tighter bound. Why do we want to move to log base 2?
So if you have a binary tree of n nodes, then you know that you require at least log n to the base 2 height. The height, if you have a binary search tree, then okay. So any binary search tree on n nodes must have a height that is at least log n to the base 2. Right. So now we are saying that if you look at an AVL tree, you might have slightly more height, but it's only some constant factor. So 1.4 times what is the smallest required, which is log n to the base 2. Right? Okay. Fine. So what we are left to do is now to show that we can maintain this AVL property over insertions and deletions. We know that this condition is sufficient, And now we are going to say, we are going to show algorithmically that when you insert elements and delete elements, your AVL tree can be, this property can be maintained very easily. Okay, so the key to this, so now maintaining AVL tree, insert. So how do you insert elements in an AVL tree? How do you delete elements in an AVL tree? So what we are going to assume is that we have an AVL tree. And then let's say a new element comes, let's say A, and we want to insert it inside the AVL tree. But if you insert it, this might violate this property that the heights differ by at most 1. And then we will have to do some fixing to ensure that the height, so that this property is maintained. Right? So how do we insert an element? Insert, let's say, an element A. So what we will do is the following. We will, an AVL tree is a BST, the binary search tree, and we know how to insert into a binary search tree, right? To scan down, left or right, and so on, and follow pointers down and insert. So insert. Let's call this BST insert of A, and next we are going to say rebalance. So let's look at an example, maybe okay. So let's this, does this satisfy AVL property? Is this an AVL tree? Yes, right. So the height of this guy is 0, 0, 0. The height of this guy is 1. The height of this guy, height 2. So this is height 1, this guy is height, which is max of these two quantities, which is plus 1, which is 3. Right? So what you could do is, to make it cleaner, is to have have dummy nodes for the leaves, and impose that the dummy nodes have, right, minus 1. Okay. So this is just makes everything cleaner. You don't have to take care of boundary conditions. So you can just insert dummy nodes at each leaf and say that their height is minus 1. Okay, so now let's insert something. What would you like to insert that will mess things up? Maybe 11. Okay, so let's say we insert 11, and what happens is 11 is smaller than 20, larger than 10, smaller than 15, smaller than 13, right? So 11 sort of sits here, right? Now you see that the height is, you get an imbalance here, right? So the left child, so what happens to the heights? This has a height 0, this guy's height goes up by 1, this guy's height goes up by 2. Now you have two children whose heights differ by more than 1. So you've lost this AVL property after inserting this 11. Okay. So what we could also maintain at each node is, which side is heavier, right? So we could either say, so for this guy is balanced, right? So both his children have height -1. So this guy is balanced. This guy, the right child has height -1, the left child has depth 1. So we could say that we could put a symbol L which says that it's leaning to the left. So this guy also is leaning to the left. This guy is balanced. So let's say we use symbols L, O, and R. Say if it's left, if the left child has higher depth, the right child has higher depth, or if it's balanced. Okay. So this guy is balanced. This guy is tilted to the right. This fellow is tilted to the right. This guy is tilted to the left. Okay. So now we inserted 11. Before we inserted 11, the tree was an AVL tree. Now we inserted 11, and now we are in trouble. Okay. So the AVL property is now does not hold anymore. Okay. So the key to rebalancing is what is called rotation. Which is the following. You take a node, say X, I hope this is right. Let's say call this A, B, and C. Suppose the picture is like this, then a left rotation around X is the following. So suppose your tree looks like this. X is a node, Y is a node, and the subtree rooted at the left child of X is a subtree called A. The left subtree of Y is called B, and the right subtree of Y is called C. Now, the operation of left rotating around X gives you the following. So Y goes up here, X goes down. Is this correct? I hope. A comes here, B comes here, and C comes here. I hope this is right. Yeah. Okay. So this is left rotate, and the reverse operation is called right rotate around Y. The key property of rotation is this. Okay. So the claim is that, say, left rotate around X maintains the BST property. So if you had this, if this tree was a binary search tree, which means that everything on the left is smaller, everything on the right is smaller for every node, then after you left rotate, that property is still maintained. So you don't violate the property that this tree is a binary search tree. Right? This is the important thing, right? Because we want to use it to search, and this we can sort of stare at it and convince ourselves that that's true. Right? Everything here is smaller than X, and this guy remains a left child of X. Everything in B is larger than X, because B is, to the right is in the right subtree of X. It lives in the right subtree. Everything in the right subtree is larger than X, so this is larger than X. And now B becomes the right. The entire subtree B sits here, so we're still fine. And C is the right subtree of Y, and everything in C was larger than Y anyway, and so we're okay. And also among X and Y is larger than X, and X is moved to the left, so we're okay. Right? So visually you can sort of convince yourself that if you left rotate, you don't mess up anything. and similarly if you right rotate. Okay, so the key operation is rotation. Okay, so how do we maintain this balance? What we are going to do is essentially look at the node, the lowest level node, okay, or the node with the minimum height, which is unbalanced. We are going to look at the node with the minimum height that is unbalanced, and we are going to apply rotations. Okay, and a constant number of rotations, either one rotation or two rotations, are sufficient to balance that node. So then the lowest height node that is unbalanced, the height of the lowest height node that is unbalanced has gone up. So we propagated this thing upwards, and now maybe there is a node higher up in the tree which is unbalanced, and again we do this rotation, either one or two, and now the lowest node that is unbalanced has moved up. We do this, we know the height was log n, so in log n steps we propagated this the lowest unbalanced node all the way up to the root, and then we do balancing, and then we are done. Each balancing step requires either one balancing or one rotation or two rotations, but it's a constant number of rotations, and as you can see each rotation is a constant time operation, right, because it's just moving around 2 or 3 pointers. So each operation is a constant time, each rotation is a constant time operation. We are only going to do one or two rotations in each step, and we are going to propagate the minimum unbalanced node all the way up. And because the height was log n, in log n steps the tree will become balanced, and each balancing operation is either one rotation or two rotations. That's it.
So the first rotation will be about the node with the minimum height.
Yes. Okay, so I'm going to do this. Okay, so rebalance. So what is rebalance? Okay. So I'm just going to do it informally. Start with lowest height node that is unbalanced. Okay, start with lowest height node that is unbalanced. Then either left rotate or right rotate until balanced. Okay, and then essentially repeat this. And okay, so I've written this in a sloppy informal manner, but I hope the idea is when it's clearer to explain it to a picture. Right, so what would you do here? So 15 is the lowest node that is unbalanced, and we know that it is unbalanced to the left. Right, we know it's unbalanced to the left. So what we could do is right rotate. Right, so after we right rotate, what would happen? So this part will become. So if you right rotate, y is 15, so y goes down, right? So 15 goes down. The left child of 15 goes up, which is 13, right? Now A remains A, so this remains 11, and now C is empty, so so we don't do anything, and this is it, right? So this is it. So this is the balance that we do. Once we balance here, then I think that the whole tree is balanced now. In this example, the unbalanced, now every node is balanced, it doesn't propagate up. So one could easily construct examples where this, once you rebalance here, then this unbalanced node propagates up, and we'll have to rebalance all the way up.
Do we need to maintain height information at each node?
Yes. Yes. But that you could do, right? I mean, you could. Okay, so what do we have to prove? So we want to prove that if the tree was an AVL tree, then we want to prove that after this one or two rebalancing operations, the subtree that node would become balanced. So the subtree router of that node would be balanced, which means that it would have this height difference of at most 1. So this is what we need to prove, right? So how do we prove this? Okay, I'll take this off. So there are two cases to consider. So case 1 is when this guy is balanced, when x's right child is balanced, or okay. So the first case is when x is right heavy, which means that so it is unbalanced to the right, and the right child of x is either balanced or is right heavy. Okay, so which means y is also unbalanced to the right. Okay. The second case is the same thing. When y is left heavy, in which case there is something. Okay, so maybe I did just do that. So there are two cases to consider. So I mean, the other case is symmetric when x is left heavy, in which case you would do the other cases are symmetric, right? So when x is left heavy, which means unbalanced to the left, right? So those cases are symmetric. So we are only considering the case when without loss of generality x is right heavy, which means that it's unbalanced to the right, and the right child of x is also right heavy, or is balanced. Okay, so then we claim that after one rotation it's going to be balanced, right? So let's look at these numbers.
This case too possibly because height of left child of x is 2 less than 3.
No, these are just some subtree. This is okay. So first of all, these are subtrees, so we don't know the heights of these things. The second is that we're going to say if the tree is unbalanced, then if the tree is unbalanced and it looks like this, where z is left unbalanced to the left. So this can happen this may not happen at the leaf, but it can happen at some internal node. Okay, So this can happen at an internal node. Okay, so can I just take 2 more minutes if you don't mind? Okay, so this can happen at internal nodes. Can happen at internal nodes. Okay, so in this case, let's look at the heights. So this is k minus 1, let's say k minus 2. This is k minus 2, this is k minus 3 because y is say balanced. X is the lowest node that is unbalanced. So everything, if y is certainly balanced, if this if x has height k minus 1, y has height k minus 2, then this guy has height say k minus 3. So x is unbalanced. So the difference did I do something silly? Oh, this is smaller than k minus 3. Right? The height, this height should become smaller than k minus 3 because x is the first node that is unbalanced. So y is balanced, so this difference is 1. Right? This is strictly smaller than k minus 3. Okay. So now let's say we do a rotate. X A B C, then what happens to the heights? What happens to the heights?
Y's height has to be more than that of its child nodes. So the B or C sub T's B height.
These guys, B or C?
Yeah. So C's root has k minus 2 height.
Yeah.
So Y's height has to be more than that. Height of Y is also written as k minus 2.
Ah, okay. Sure. So this is k minus 1.
The upper one will have k.
Okay, so let's say this is okay. Let's say this is k. So this is less than k minus 2. So if x is unbalanced, right, and x is right heavy, which means that the right side has higher height than the left side. So this is smaller than k minus 2. Right. So let's say this is k minus 2. This is k minus 1. And y is balanced, right, and y is right heavy, so the right height is more than the left height, so this is k minus 2 and this is k minus 3. So we are going to assume that we are in this case. Okay, so now let's see what happens after we rotate, what happens to the heights. So you see what has happened, C has moved up, right? So C has a height now of, no, so what has happened?
Height of C remains same.
Height of C remains the same.
Y's height also remains the same.
No, Y goes up, right? Y goes up, so this goes down. Okay.
C is k minus 2,
Uh-huh.
and B is k minus 3, A is still k minus 2.
Okay.
Next therefore is k minus 1,
Yeah.
y minus k.
Yeah. Right. So this, now you get balance. Right. So properly. K minus 1. Okay, and okay, so one rotation we'll balance it, and you can check that this happens even when y is balanced. Right? The situation here is slightly more complicated, but it's essentially a matter of just sort of putting these numbers and staring at what happens. So in this case, I guess what you need to do is to left rotate around z and then right rotate around y. So left rotate around z and then right rotate around. So you need two rotation operations, but after this you can show that in this case you're balanced. So this you can work it out. It's essentially just putting the heights and checking what happens when you rotate. Okay, so that's that, and this shows that after you so at least the subtree rooted at x now is balanced. So any unbalanced node now is at a higher level, and now you propagate this, and therefore you can do insert in log n steps. Right. So now we've shown that insert takes in log n steps we can do insert, because what we do is we insert, then we look at the lowest level node that is unbalanced. We know that one or two rotations are sufficient to balance it, and now the lowest unbalanced node has propagated up. We know that one or two rotations are sufficient to balance it. Then we keep moving up, and in log n steps we reach the root, and now the whole tree is balanced. Okay, so sorry, I sort of messed up a little bit here, but I hope the overall idea is clear. Okay, thanks. So we'll take a break and come back.
So any questions? Why do we prefer to teach RBG and
Oh, I don't know. It's I mean this is
more efficient and easier?
so in practice. I think AVL trees are people believe that red black trees are more efficient than AVL trees. The reason.
The factor is I think 2 log.
Okay, so the height. Yes.
Insertion and deletion in RBTs are comparatively simpler because whenever you're inserting below any black node, so there you don't have to do anything. You can see there's roughly 50% probability the new node that you're inserting is just going below a black node, not disturbing the factor at all, and it won't perform anything. So for large number of cases, the insertion in the RBT is just an insertion in the normal BSC.
I think there will be more adjustments needed in this.
Yes. So AVL tree. Okay.
So comparative predictions are more.
So what happens is that your condition here is that the height difference is 1, and this is a stricter condition. Therefore, the number of rotations required per insertion and deletion is more. Therefore, you spend a little more time compared to red black trees. So in practice, if you implement, red black trees will probably take less time to insert and delete than AVL trees. But AVL trees are certainly, at least I think, are much simpler to teach, and essentially the key is rotations, and I think.
And for searching related tasks, we can always go for AVL.
I mean they play the same role. AVL trees, red black trees, 2-4 trees, all of them play the same role. You want to search, you want to maintain a linearly ordered set, and you want to maintain it over insertions and deletions.
Being more the constant involved in the AVL is that we are able to do the mathematically smaller than the constants involved.
The height, yes, sure, the height one is smaller, but the insertion deletion times are longer because the number of rotations required are more compared to red black trees.
Go for AVL kind of.
AVL, red black, whichever.
Also, all the balanced trees, like even 2, 3, 4 trees and 3 trees, whatever, they all are balanced. So, which gives the best performance for searching and insertion overall?
Oh, I don't know if as far as I know that AVL trees, red black trees perform take less time per insertion and deletion than AVL trees. That's what we know. And 2-3 trees or 2-4 trees are sort of red black trees are a special case of 2-4 trees anyway. So that's.
Can we have your comments for comparing skip list, a randomized skip list, or a balanced search tree? Why do we
place more importance in trees?
Skip list, well, okay, so first of all, skip list is a randomized data structure, right? So you know, so you don't have any,
We expect that it would be balanced.
yes. So I mean, obviously, so sure. So I mean, you can also prove that with high probability it is balanced, but it's, you know, it is still something that is true with less high probability is still less desirable than something that is always true, right? So if you want, let's say, an application where you want the insertion and deletion to take, let's say, you know, some fixed amount of time. So therefore, you want to guarantee that the insertion deletion times are, let's say, log n, whatever log n is. But a skip list does not guarantee that. There is a very small probability that it might take a long time to insert. Sure, it's a very, very small probability. It may never have.
Is it good enough? I mean,
Sure.
other than trees, maybe?
It's much simpler to implement. It's much simpler to implement, but if you're not happy with expectation bounds, you're not happy with the fact that, say that on average the height is something, you know, on average it takes so much time, you want a guaranteed bound, then maybe you don't want a randomized data structure. Right? So you also don't know, you know, then you want to ensure that your random number generator is good enough and all of these other complications arise. So, yeah.
Okay, so we'll have a shorter period today, and let's try to be back within 10 minutes, say by 11:35 to be starting.